In this video, we're going to be proving the derivative for the cotangent function, which is equal to negative cosecant squared theta. We're going to be doing this through the definition of the derivative for any given function of x, which is the limit when h goes to 0, representing our change in x, of f of x plus h minus f of x divided by h. With this definition in mind, we can apply f of x for the cotangent function, which is equal to the limit when h goes to 0, by definition, the cotangent of theta plus h minus cotangent theta divided by h. We can further evaluate this limit to be equal to the limit when h goes to 0 of cotangent of theta times cotangent of h minus 1 divided by cotangent of theta plus cotangent h minus cotangent theta divided by h. And all I did here was apply a trigonometric property of the sum of two angles for the cotangent function represented by theta and alpha. This is equal to the cotangent of theta times cotangent of alpha minus 1 divided by cotangent of theta plus cotangent of alpha. This is a trig property that we're going to be needing to prove this limit. So with this trig property of the sum of two angles for cotangent theta, I've expanded the cotangent of theta plus h as such to obtain the following limit. And what we can do now is further evaluate this limit by combining the numerator and simplifying this entire fraction to be equal to the limit when h goes to 0 in the denominator h times cotangent of theta plus cotangent of h, and in the numerator cotangent of theta times cotangent of h minus 1 minus cotangent squared theta minus cotangent theta times cotangent of h. And how I obtain this is by first combining the two terms in the numerator, which is the first, the expanded form for the cotangent theta plus h, and the second term, negative cotangent of theta. To combine these two terms, we must obtain a common denominator of cotangent of theta plus h, which is present in denominator right here. And in the numerator, I've simplified the cotangent theta times cotangent theta plus cotangent h to be the following of negative cotangent squared theta minus cotangent theta times cotangent of h. This is the result from cotangent theta times our common denominator of cotangent theta plus cotangent h. And also, we combined it with our previous term, which is cotangent theta times cotangent h minus 1. So we combine these two terms to obtain this grand limit right here. And what I can now do is further simplify our numerator because we have two like terms. Those two terms are the cotangent theta times cotangent h right here and negative cotangent theta times cotangent h right here. So we can cancel these two terms out to become, if I scroll down, the limit when h goes to 0 of negative 1 minus cotangent squared of theta divided by h times cosine of theta, or cotangent of theta, plus cotangent of h. And what I can do is rewrite the numerator to become the limit when h goes to 0 of negative 1 plus cotangent squared theta divided by h times cotangent theta plus cotangent h. And now I can apply a trigonometric property, which is the Pythagorean property, which states that 1 plus cotangent squared of theta is equal to the cosecant function squared. So we can rewrite this limit's numerator to be equal to the limit when h goes to 0 of negative cosecant squared theta divided by h times cotangent of theta plus cotangent of h, as so. And now what we can do is apply a limit property of the product of two functions. So the limit when our input of x approaches to any number of n of the product of two functions represented by f of x and g of x will be equal to the limit when x approaches to n of our first function, f of x, times our second function, the limit when x goes to n of g of x. And relative to this specific limit, our f of x function will be equal to negative cosecant squared theta, and our g of x function will be equal to 1 over h times cotangent theta plus cotangent of h. So with that, we can break up the limit to be equal to the limit when h goes to 0 of negative cosecant squared of theta times the limit when h goes to 0 of 1 over h times cotangent of theta plus cotangent of h. And now what I can do is I can take out negative cosecant squared theta outside of this limit, because negative cosecant squared theta relative to this limit is a constant. And I can do this because of another limit property, which states that the limit when our input of x approaches to any number of n of a constant represented by c will be equal to that constant. And the reason why we can treat negative cosecant square theta within this limit as a constant is because this limit has to do with our change in x represented by h. When h approaches 0, it is not affecting the theta value because the theta value and the h value are two completely separate variables. Therefore, since the h quantity which is changing does not affect the theta variable, we can treat negative cosecant square theta altogether as a constant. So this becomes the negative cosecant square theta times the limit when h goes to 0 of 1 times the limit when h goes to 0 of 1 over h times cotangent theta plus cotangent of h. So what now we can do is we can further evaluate this limit right here from this property of limits, which is the limit of a constant is equal to that constant. And since our constant is 1, this limit evaluates to be equal to 1 altogether. So if I scroll down, will become equal to negative cosecant squared of theta times the limit when h goes to 0 of 1 over, if I rewrite the denominator, h times cotangent of theta plus the cosine of h divided by sine of h. And the reason why I can do this is because of a trig property, which states that the cotangent of theta can be rewritten as the division of cosine of theta and sine of theta. So I've rewritten the cotangent of h to be cosine of h divided by sine of h. So what I can do now is further simplify this entire ratio by simplifying the denominator and combining the two terms of cotangent theta and cosine h over sine h. So this becomes negative cosecant squared of theta times the limit when h goes to 0 of sine of h in the numerator and denominator, h times parentheses cosine of theta times sine of h plus cosine of h. And the reason why I can do this is because when I first combine cotangent theta and cosine of h divided by sine of h, I give it a common denominator of sine of h. So this denominator becomes cosine of theta times sine of h plus cosine of h divided by sine of h. And since it's h times this entire quantity, we can move the denominator sine of h into the numerator, obtaining this limit as such. You can check my arithmetic later on. But moving on, we obtain negative cosecant squared theta times the limit when h goes to 0 of sine of h over h times the limit when h goes to 0 of 1 over h times, or rather, cosine of theta times sine of h plus cosine of h. And how I've broken up this following limit right here is from a previous limit property, which is the limit of the product of two functions represented by f of x and g of x. So I've broken up this limit as such because within this specific limit, I've treated f of x to be equal to sine of h over h, and our second function g of x to be equal to 1 over cosine of theta times sine of h plus cosine of h. Therefore, I've broken up this limit to be the product of these two limits. So with these two limits, we can apply another limit property to evaluate this limit, the limit when h goes to 0, the sine of h divided by h. That is the limit when an input of x approaches to 0 of sine of x divided by x is equal to 1. This limit property is especially useful for proofs of derivatives. Likewise, in this derivative, we'll be proving this limit in future videos, but for now, accept this limit as true. So because we have this limit, this entire thing, sine of h divided by h of the limit when h goes to 0, will evaluate into nothing more but 1. And to evaluate this limit, all we do is apply h is equal to 0 into this ratio. So this limit becomes 1, and what this limit becomes is 1 over cosine of theta times 0 plus 1. And the reason why for this is because sine of 0 radians is equal to 0. 0 times cosine of theta right here. And the cosine of 0 radians is equal to positive 1 right here. And we know that 0 times any quantity, such as cosine theta, will result in 0. So 0 plus 1 will be 1. 1 divided by 1 will be equal to 1. So this limit is equal to 1, and this limit is also equal to 1. So we can now further rewrite this equivalent ratio for the cotangent theta's derivative. This becomes negative cosecant squared theta times 1 times 1, which is equal to negative cosecant squared theta. Hence, proving that the derivative for the cotangent function is equal to negative cosecant squared of theta.